Hello, everybody. Welcome to chapter 6 of particle nuclear physics. Today, we're going to be taking a look at the first of the standard model theories, which is QED, which describes electromagnetism. Okay, so what we're going to be doing here in this section is having a look at gauge invariance and what that means in terms of QED, and what that means in terms of the allowed vertices that we have in these theories. So we'll be discussing our Feynman diagrams as well and going through some examples. Then we'll have a look at scattering with the electromagnetic force, which you should be quite familiar with by now. And then looking carefully at the experimental tests of QED and how this has been verified. And actually, it's been verified to very high precision. And then we'll finally look at the coupling constant of the electromagnetic force and how it's actually quite badly named. All right, so let's start off with QED. Quantum electrodynamics, and it's the gauge theory of electromagnetic interactions, so with charged particles and photons. So if you consider, for example, let's start off with something you know about. When you have a charged particle moving through electromagnetic field, it interacts with both the electric and the magnetic parts to experiences a force proportional to its charge, and that force makes it moved in a curved path. Or if the magnetic field is zero, it'll accelerate it. Right, so what we have, if you remember Maxwell's equations, are electric and magnetic fields are actually described in terms of vector and scalar potentials here, A and phi, which hopefully you're familiar with. And here are your Maxwell's equations. And they can be put into a classical Hamiltonian to describe the electromagnetic interactions. Now, if you consider an electron, a simple charged particle, moving through an electromagnetic field, it experiences that force. It experiences a change. Its field, if you want to treat it like a field instead of a point-like particle, that field changes. Now, if you're going to have any change in this electron's field, it requires a change in your electromagnetic field to conserve your gauge invariance. That change is simply the interaction of the electron via this virtual photon emission. So that's virtual and it has to go and do something else. Right, so let's have a look at the Schrödinger equation as you know it with your vector and scalar potentials describing your electromagnetic field. If you make a change to the electron, i.e. to this wave function here, of some local gauge transformation, so some transformation that depends on the spatial and time coordinates here, quite a simple transformation here. You'll find that you only have gauge invariance. This Schrödinger equation only holds true if there's also changes to your vector and scalar potentials. Now you can see this in Appendix E. Please do go and try through it. Do go through it in detail. It's quite interesting. So if your wave function here changes, your vector and scalar potentials must also change so that the Schrödinger equation holds true. So how they change, you can see in Appendix E, you have some small change to your vector potential that depends on your gauge transformation itself, and then you have a change to your scalar potential. Again, that depends on the first time derivative of this gauge transformation. So this change to your electromagnetic field is the photon. If you make a change to a charged particle with the electromagnetic force, you require the existence of another particle. You require the photon, and this is your physical gauge field. And this gauge field that QED predicts, the photon, completely specifies the nature of the electromagnetic interaction between your charged particle and the electromagnetic field. And so the nature of this new gauge boson is that it's massless. We know photons are massless. You need the range of the photon to actually be infinite to make some cancellations over space-time. And another thing that comes out is that electric charge has to be conserved. We've introduced this gauge symmetry, i.e. that we want the Schrodinger equation to hold true when we make a change to a field. To do that, we have to introduce a photon, and according to Noether's law, we need some conserved quantity, and that's electric charge. So the charge, or the electron's charge in the example that we've been given, interacts with the electromagnetic field via a photon, and its charge does not change. So your total charge does not change in space or time. So QED, quantum electrodynamics, is a gauge theory. Now, for this course, you do not need to know all the details of such things as a local gauge transformation. I am showing you for completeness. This will be tackled fully in the Part 3 course. So let's have a look at our electromagnetic vertex for our Feynman diagrams here. We can have any charged particle in the standard model, whether it be unit charge, electron, muon, tau, or our fractionally charged quarks. They can emit a virtual photon. So if you want a full physical process, there has to be another vertex here, of course. The charge of that particle is unchanged. So this is conserved throughout these electromagnetic interactions. And also the flavor of the particle is unchanged. And you can have all those rotations of these vertices that I went through in the previous chapters, where you can have the photon pair producing your charged particles, or you can have a particle or an antiparticle annihilating into a photon. So you can have all the rotations of this. Now, the strength of the interaction here, this coupling constant here, we've called it QE. This is proportional to Q, the charge of the particle that the photon is interacting with. So it's going to be stronger for the unit charge particles and a bit weaker for those fractionally charged quarks. We're not going to violate our well-known energy and momentum conservation or angular momentum laws. Parity and the charge, as I said, are always conserved in this. So you're not going to violate any of those. And as I said, that never changes the particle type or flavor. An electron is still an electron after it absorbs or emits a photon. Only the W boson can change flavor. So let's have a look at some important QED processes that you may have come across already in your undergraduate degree. This is Compton scattering, where photons and electrons scatter or interact with one another. We can draw two lowest order Feynman diagrams here, both the S channel and the T channel diagrams. In the S channel diagram, we've got the photon being absorbed by the electron, and then we have a virtual electron here in this internal line. We can never actually probe that virtual electron. All we can probe is the scattering products here. So then the virtual electron emits the photon, and these are both real particles. So two vertices here for our lowest order Feynman diagram. But we can also draw another lowest order Feynman diagram. So don't just stick with one. Consider your S, T, and U diagrams. We don't need to consider the U diagram here because these are not identical particles. So in the T channel diagram here, an electron here could give off a photon, and then we have a virtual electron that could absorb that photon. Or we could have this photon pair producing an electron and a positron, which then annihilates down here at this bottom vertex. And with Feynman diagrams, we draw all time ordering. So this internal line is vertical. These two vertices are on top of one another to denote both time orderings that I've just described. So with these Feynman diagrams, we can then write down a matrix element as the product of the couplings at all of the vertices. So we've got unit charge in all of these cases, so we know it's going to be proportional to E squared. And then if we want to try and calculate cross sections from this or scattering rates, those are going to be proportional to the matrix element squared. So these cross sections, the fundamental sort of strength of this interaction is proportional to e to the power of 4, or if you want to understand it in terms of the fine structure constant, which is 1/137, it's proportional to alpha squared. So you can have a look at your problem sheet, which has a look at higher order diagrams in terms of alpha square alpha. One other common QED process is Bremsstrahlung, where an electron emits a photon in the presence of matter. So if we had an electron in a vacuum emitting a photon and staying as an electron, we did this in the chapter 4 in the standard model. We showed that that's not a real process. One of those particles has to be virtual. Something else has to happen to it. It has to remain an internal line. And so this is what's happening here. We've got an electron radiating a photon in the presence of matter. And I've popped a nucleus here because they're quite highly charged. So we have an electron emitting a photon, and then we have a virtual electron, which then exchanges a photon with a highly charged nucleus. And then it becomes a real electron. So we've got two virtual particles here, the electron or the photon. And I've got these vertices here, all vertical. And these internal lines, all vertical for a good reason, because we don't know if this vertex happens first or this vertex happens first. So you can probably draw two diagrams here where we have a photon emitted from the nucleus and pair producing, and then an annihilation here, or the one that I described where you have this emission here and then absorption here. So we have three vertices here. Two of them are factors of E, and this one depends on the charge of the nucleus. So I've put Ze here. The more highly charged the nucleus, the higher this coupling will be. And so the matrix element here, if you have a look at the product of all of these three vertices, is Ze cubed. You can put that into your cross section, so you'll have this proportional to Z squared in e to the 6, or if you want to put that in terms of alpha, alpha cubed. In the same way, and I think you have yes, you do. You have a problem on your problem sheet about this, a photon pair producing into an electron and a positron. Again, in the same way as an electron emitting a photon or absorbing a photon, that cannot happen in a vacuum because you would need a virtual particle on one side or the other. So something else has to have happened. So there has to be at least two vertices in these Feynman diagrams, essentially. So what about a photon? As it travels through matter, it can pair produce an electron and, say, a virtual positron here, which can exchange a photon with a nucleus in matter. And again, there's these three vertices, and we have vertical lines drawn here to denote all time ordering. There's no problem with drawing a particular ordering as long as you see that you need to have all time ordering, and you can just redraw it again afterwards, or draw it in pencil and rub it out. So we actually have almost the same Feynman diagram here, actually, as this Bremsstrahlung diagram. Instead of an incoming electron, we've got an incoming photon. We have a photon and an electron here in the final state and an electron-positron pair here. We've got the same vertices involved here, and also the same internal lines, so you can expect the cross-section for this to be very similar to the Bremsstrahlung cross-section. Okay, some more electron and positron annihilation, or particle, antiparticle annihilation. And this is what happens in such colliders as LEP, where we collided electrons and positrons. They can annihilate together to form a photon, and the photon can produce another pair of charged particles like a quark and antiquark. And so here we cannot have a T-channel diagram. We can just draw an S-channel diagram for this because there's no T-channel diagram. There's no vertex, for example, that will change an electron into a quark like this. There's no such vertices as these. That's not allowed. So we've only got the annihilation and then pair production diagram, this S-channel diagram. So the coupling constants here are important for our matrix elements. We've got a factor of E squared, but then these quarks are not unit charged, they are fractionally charged. We're going to have to take those into account. So our matrix element will be the charge of whatever quark pair has been created here, multiplied by E squared. Again, you can put that into your cross section as well and try and understand this in terms of the charge of the quarks that you're producing and alpha. Finally, pion decay. Just looking at some hadrons here. So up and anti-up can form a bound state called a pion. They're very low mass. They're about 140 MeV. And these pi zeros, if you remember when we discussed colliders, they decay very quickly into two pions via the electromagnetic force. They cannot decay, they cannot annihilate into just one photon, and I'll prove that to you later. What you end up doing is violating total angular momentum. This is a spin 0 particle, and it cannot produce a single spin 1 particle. You'll violate total angular momentum there. What it has to do is produce two photons, two spin 1 particles. And so what we have is one of our quarks emitting a photon, and then we have annihilation down here. Or we could have this photon emitted first and annihilation here. So we have a vertical line here to denote all time ordering. So we have two vertices here, both a factor of E for the electromagnetic force, and we need to denote the charge of the up quark here, which is plus 2/3. So two vertices, the charge of the up quark squared and E squared. And again, you put that into your cross section as the matrix element squared, and you have this up quark, the factor of 4, alpha squared. One last one, which is the J psi decay. The J psi is a spin 1 meson. We will get into all of these, I promise. And it's a bound state of a charm anti-charm quark. Now, since it's a spin 1 particle, it can annihilate its quarks. It has the right spin configuration, essentially, to annihilate into a spin 1 boson. And so we can have this annihilation vertex here, which we didn't have with the pion. So we have the charm anti-charm annihilating into a photon and pair producing a couple of muons. And so we have two vertices here, one with the charm charge times E, and one with just a factor of E because the muon's a unit charge. And again, we can build our matrix element and our cross sections. Okay, so what we're going to do next is have a look at scattering with the electromagnetic force in QED. We're going to calculate the cross sections for two different processes. The first one is going to be electron-proton scattering, and we can consider this as quite a low energy interaction where that photon doesn't have the energy to probe the structure of the proton. So quite a low energy photon we're going to assume here, so we're not going to draw all of the different constituents of the proton. The other one we're going to consider is an S-channel diagram where we're colliding electrons and positrons. They annihilate to a photon and give us our muon pair here. Now take a look at these diagrams. They're different shapes. We've got a T-channel diagram here and an S-channel diagram here. We've also got different initial and final state particles, but in both cases, we have a photon as the internal line, as our propagator. And in both cases, we have two electromagnetic vertices, both with charge Q, both with strength QE. So what we're going to do to calculate these cross sections, we're going to use Fermi's golden rule and the Born approximation here to calculate the differential cross sections. So we're going to need the matrix element here. For both examples here, the matrix element looks the same. We have our factors of E squared for both of our diagrams, and then the propagator at the bottom will be Q squared minus M squared. The mass of the photon there is 0, so it's just Q squared. Now, since we have a T-channel diagram here and an S-channel diagram here, the calculation of the invariant mass of this photon is different. And here, this T-channel diagram, it will be the difference in these two 4 vectors between the final and the initial state 4 vectors for the proton and the electron. Whereas here, because we have annihilation, it will be the sum of the two initial 4 vectors. So we're going to have a look at that next. Right, so let's just have a look at the electron-proton scattering first. And I'm going to draw the diagram for you again because it's good practice for me and for you. So we have an electron coming in. It's going to exchange a photon with a proton. Okay. We're going to label that photon there, and I'm going to label our vertices here as E and E because they're unit charged. Right, so our matrix element, just looking at our Feynman diagram, we can have a look at that. It's the product of our two, it's the product of our two vertices here, E squared over Q squared minus M of our photon squared, and that's 0. So it's just E squared over Q squared, quite straightforward. The next thing we need to do is calculate the invariant mass of this photon. Okay, in terms of the energy of the initial and final state, either electrons or protons. They are, because of conservation of energy and momentum, they'll be the difference between the proton 4 vectors. It'll be the same as the difference between the electron 4 vectors. So it's a T-channel diagram. Let's have a look at this. Our Q squared, we're going to need to calculate the invariant mass here. So we're going to have a look at the difference between these two 4 vectors. So it will be the final state electron energy minus the initial state electron energy squared minus the final state momentum minus the initial state momentum all squared. Now this is different where we summed them all before. We're literally taking the difference between 4 vectors and not summing them this time. So for an S-channel diagram, you would be summing these two components. So let's have a look at that. That's going to be, oops, that's going to be EF squared plus EI squared plus, oh, minus, getting ahead of my 2EI, EF, minus PF squared minus PI squared plus 2PF PI. I'm getting this right. Good. So here we've got, again, as usual, mass terms for our final and initial states here. The energy squared minus the momentum squared is the mass squared. And since we're talking about either electrons or protons here, they're both the same masses, aren't they? So we've got 2m, I'm just going to call it m squared, minus 2EIEF, and then we've got 2, I'm just going to deal with this momentum part here. It's the dot product of these two vectors, I, F, cosine theta. There we go. So what I'm going to do is put us in a sort of slightly higher energy situation where we can neglect the mass of the electron. They're so light, they usually can be treated as massless, and that means their energies are equal to their momenta, the absolute values of their momentum. And then this simply simplifies to minus 2EI EF 1 minus cosine theta, because these momenta, these absolute momenta, are the same as their energies if we can treat these electrons as massless. And then we can put that into the half angle formula as well, if you so wish. EI, EF, sine squared theta over 2. That's F. Okay, so when we put this into the Born approximation or we can put this into our matrix element here and the Born approximation for the differential cross-section. So let's remind ourselves of that. Our differential cross-section here, the thing that we're trying to calculate, it's E squared over 2 pi squared. If you have no idea where this is coming from, please go back to chapter 2, where it was derived, times the matrix element squared. So, right, we now have everything for our matrix element squared with our Q squared. So we've got E squared over our 2 pi squared. Okay, so our matrix element squared needs to go in there. So our matrix element squared is E to the power of 4, Q to the power of 4. I'm going to do a substitution quickly. If you remember, Let me check this to get it right. Squared over 4 pi, good. We know that the fine structure constant is E squared over 4 pi, and I'm just going to replace in here for that so that we've got 16 pi squared alpha squared over Q squared. Q to the power of 4. Okay, so this is what we want to pop in here. We've got our 16 pi squared, alpha squared, and q to the power of 4 here. So we've got 16 ei squared, ef squared, sine to the power of 4, theta over 2. Okay, we can do lots of wonderful cancellations here because this is the initial state energy, of course. So we're going to have some cancellations here. So after you cancel your factors of pi, etc., you've got alpha squared over 4e squared sine to the power of 4 theta over 2. So we've calculated this from a Feynman diagram. So this is what we call our quantum electrodynamics. I'm not writing Latin here. This is the result we get from quantum electrodynamics using having a look at our Feynman diagram for electrons scattering off of protons, calculating our matrix elements based on this internal line, treating it as a virtual photon with some invariant mass that is not equal to its physical mass of 0. We're popping this into the Born approximation for the cross-section, calculating our invariant mass of that photon. And we actually end up with exactly the same result as Rutherford scattering. That was calculated with classical mechanics, or at least relativistic mechanics. So QED, this gauge invariant theory, this gauge theory produces the same result that we're used to from basic Rutherford scattering. So you can see it a little bit more neatly there. Right, and this was quite important, this electron proton scattering, in the discovery of quarks. So the photon, when we're scattering, I'm just going to draw the diagram again here. When we're scattering an electron off of a proton, they're exchanging a photon between them. Okay, and the photon is hopefully going to carry lots of form momentum, lots of energy and momentum. The larger the energy and the momentum, i.e. the larger the invariant mass of this photon, the smaller the distance that it can probe. So if it's quite a low q squared, a low invariant mass virtual photon, it's going to see the proton as a point-like particle. And we'll see cross-sections that look like the Rutherford scattering that we're so familiar with. Now, if you increase the energy of your electron that you're firing at the protons, you will increase the q squared of this photon. You'll increase its invariant mass. It will have larger energy and momentum. It will be able to probe smaller distances. So as it increases, it'll start to see the structure of the proton, or at least start to see some of the more excited states within the proton. And this is what happens, for example, with Mott scattering, where we've got those higher energy electrons. It starts to deviate away from what we would expect the scattering off of a point-like particle to be. And in fact, if you can fire your electrons at high enough energy, the invariant mass of this photon is large enough to probe the distances on the sizes of our quarks here. And your electron, instead of interacting with a proton, will start to interact with up quarks, or a couple of up quarks, or down quarks. It'll start to have a small enough wave length, essentially, to probe this kind of structure. Then you'll have scattering instead of off of the composite particle, the proton, off of the constituents, off of the quarks. And this is what happened in Hofstadter's experiment when he did very high energy electron scattering. The rate of scattering actually dropped below that of Rutherford scattering. The coupling here to the up quarks, we know, is lower because they're fractionally charged. It'll be their charge of the up quark times E. And so you expect the cross section to be lower. And so this is one way that we basically discovered quarks. We saw that the proton had structure. When we increased the energy of the photon being exchanged between the electron and proton, we saw that the proton had structure. So it's a very important interaction, electron-proton scattering. The next one we're going to have a look at is electron-positron annihilation and the creation of muons. I'm going to do that here on this slide. You can have a look at it in the neater version. So this is a very similar diagram, but it's an S-channel diagram. Different particles are involved, and we've got the same vertices. So we've got E plus, E minus annihilating into a photon. And then this photon can pair produce our mu plus and our mu minus. So arrows forward in time for our particles, backwards in time for our antiparticles. And then finally, label our vertices here, E for both of them since they're unit charge. So we've got to do the same thing here. We've got to calculate the matrix element, put it into the Born approximation for the differential cross section and see what we get. So let's have a look at our matrix element. It's exactly the same as before. It's E squared over Q squared. But we now have to calculate the invariant mass of this photon, and it's different because it's an S-channel diagram than a T-channel diagram. We have to add up the 4 vectors of either the initial state or the final state particles. They should be equal since we're conserving energy and momentum here. So let's calculate Q squared. I'm going to call it E plus plus E minus so that I don't care which final state or initial state we're using. The sum of the energy squared minus the sum of our momenta squared. All right, so I'm going to assume this is done in the center of mass system just to make this calculation a lot easier. Remember, the invariant mass that you calculate in one frame of reference is the same in another frame of reference. So you can, if you're calculating this invariant mass, choose a frame of reference to make your life a lot easier. So if you choose the center of mass frame, your energies, E plus is equal to E minus. They're equal and opposite energies. They're the same particles. So I'm just going to call that E, and then also your momenta are equal and opposite. They're colliding head on. So this very simply becomes 4E squared. And so we're going to need, of course, for our matrix element, we're going to need our matrix element squared for the Born approximation, which is going to be E to the power of 4 over Q to the power of 4. So let's do this. Our differential cross section using the Born approximation, again, E squared over 2 pi squared multiplied by our matrix element squared. So we've got our E squared over 2 pi squared is, I'm going to replace E to the power of 4, E to the power of 4 with 16 pi squared alpha squared again. And then Q to the power of 4 here is simply 16 E to the power of 4. Doing the cancellations here, we have alpha squared over 4E squared. And this could be expressed in terms of the Mandelstam variable S, or the center of mass energy itself. A bit like Q here, it's alpha squared over S. Okay, now if you want to, this is a very straightforward example where we haven't accounted for the spin configuration of our electron and positron being in the correct spin configuration for our photon to be created. We've got 2 fermions here and this spin 1 boson. They could be in, for example, a spin 0 configuration. So once you take that into account, so spin effects, you get the Dirac, do that with the Dirac equation. We get alpha squared over 4s 1 plus cosine squared theta. Okay. So a couple of examples there, drawing a Feynman diagram, writing down the matrix element, putting that into your differential cross-section, and you'll need to know the invariant mass of that internal particle, that virtual particle. Okay, so we can do this, and for example, you take into account the spin effects using the Dirac equation, which you can do next year in part 3. You'll have the formula that you need for the differential cross-section for E plus E minus, creating a mu plus mu minus. And you can integrate that over the solid angle if you wish. And you can see the line here predicted by QED, predicted by this equation for the cross-section as it varies with the center of mass energy here. Right, so you increase the center of mass energy here, you expect your cross-section to go down. And we have done this scattering at many different experiments here, even at higher energies now at the at LEP. But some of the old experiments here, Jade and Mark and Pluto and Tasso here, have measured the cross-section for E plus E minus going to 2 muons. And we find very good agreement with QED. For example, if you take this data point here, if you want to plug in a center of mass energy of 22 GeV here, so 22 GeV squared in here, you can use alpha of 1/137, and you would predict from theory about 0.18 nanobarns, which is the units that we have here, and indeed that is very good agreement with what we see. So you can predict these cross sections from first principles, and you can go away in measurements, in experiments, and make these measurements. Okay, so we can also have QED interactions when we annihilate quarks, and this is called the Drell-Yan process. So if we're colliding a proton and a pion, we can have a anti-quark annihilation to a photon and producing a pair of leptons. And this is something you're going to play with in problem sheet 2 on question 14. You're also going to have lots of hadrons in the final state because you still have these spectator quarks left over from the proton and the pion here. For example, you've got 2 downs and an up. They could form, 2 downs and an up, they could form a neutron. So you could end up with a neutron and a couple of muons here. So what we need here is the annihilation between an up and an anti-up. If this pion had an anti-down, you can have a look at the annihilation of a down with an anti-down. But here we've got an up and an anti-up in each case. So they annihilate to a photon to pair produce our pions. And these vertices have a factor of E each. We've got unit charge for our muons, but we've got a reduced charge here for our fractionally charged up quarks. So you can calculate this again from first principles. If you just have a look at your cross section, this should go as it should be proportional to your matrix element squared. So you can calculate your matrix element, for example, just looking at if we ignore factors of q squared that we have on the denominator, your matrix element should be proportional to q. I'll just write it down. Your matrix element should be proportional to QU E squared. You pop that into your cross section, that's proportional to your matrix element squared. So you expect this to be QU squared E to the power of 4. And you can write that in terms of alpha if you want to. QU squared, alpha squared. I mean, you're leaving out factors of 4 pi, but it works quite nicely. There's also a factor of 2 because these 2 up quarks are distinct states. We'll go through this in QCD later. They do have different quantum numbers. They're 2 fermions. They must have different quantum numbers. They're the same charge though. But we could have the annihilation between this up quark and that anti-up quark. There's 2 opportunities. So we actually have a factor of 2 here to take that into account. So you can have a look at this with some of the examples in the problem sheets and see this yourself. All right, so next what I would like to do is have a look at the experimental tests of QED. There's, having a theory is absolutely fine, but we need to verify it, and that's how people win Nobel Prizes. Now, QED has been so successful and been tested to really, really high precision. You can do this using the magnetic moments of electrons and muons, and this should be, according to the Dirac equation, a factor of 2 for a spin-like particle. E over 2 times the mass of that particle times their spin, which is obviously a half. Now, if you just use this simple example, you actually get something different to what we actually measure in nature. This is because you're calculating here, sort of from the first principles, just the lowest order effects from magnetic moments. However, if we measure the magnetic moments and we try and extract G, it's supposed to be 2, but actually it's not quite equal to 2, because we've actually got higher order diagrams that contribute. They can constructively contribute, and they can actually destructively contribute as well. So it's quite complex. So if you consider you're going to probe an electron or a muon with some photon that you're sending in to try and measure its magnetic moment, this is the simplest Feynman diagram that you can have. But you don't actually know what's going on in this sort of black box here. We don't know. It's not actually open to us. So what could happen is actually your electron or your muon could be exchanging another photon. Or you could have something far more complex with even more vertices. And since alpha is small, it's a small perturbation, then these higher order diagrams don't matter so much, but they do have an effect. They introduce what we call the anomalous magnetic moment, that this G is not quite equal to 2. And QED can explain these with Feynman diagrams and these higher order calculations. So if we sort of normalize everything to the standard one, this is sort of going to be on order 1. This diagram has another 2 vertices here. Another 2 vertices, I'm just going to label them E. So it's got another order of E squared, i.e. alpha. And then you can go on and on and on to sort of order of alpha squared if you want to. And these diagrams with 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices have over 1,200 different configuration, different distinct diagrams that you can draw with different calculations of the invariant mass of all these invariant particles, virtual particles. So let's have a look at this. Of order alpha cubed is a little bit easier to envisage. We've got 72 different diagrams here. Feel free to zoom in and have a look at them. You may think you can think of more distinct diagrams with the same number of vertices, but usually they're just manipulations or twists of the other ones and will result in the same calculation. So for example, if we take into account all of these higher order diagrams that will contribute to the magnetic moment of an electron, we can calculate how far away we expect G to be from 2. So this anomalous magnetic moment. So our first order diagram should just give a G of 2, but the higher order diagrams contribute to a very small amount and actually change this. So experimentally, we measure this to very high precision as, let me try and get this right, 11,596,521.11 plus or minus 0.007 times 10 to the minus 10. So this is what we measure very, very, very accurately from experiment. So G should deviate from 2 by roughly sort of, you're talking about orders of 10 to the minus 6. But we measure it to very high precision, so we write it like this. Now, QED makes a prediction of this as well. You can also use QED to calculate how far away you would expect G to deviate from 2 based on all of these higher order diagrams. QED agrees with experiment to the level of 1 in 10 to the 8, which is incredibly precise. You can see these agree beautifully. And you can imagine if you had even more computing power, which we do today, this has probably actually been calculated to even higher precision. So this is a very, very precise theory. QED explains this anomalous magnetic moment of electrons and muons, why it's different from two. You have all of these higher order diagrams contributing in a very, very tiny way, constructively and destructively, but it describes what we measure in experiment beautifully. So let's have a look at these higher order terms because they can be important. So let's go back to our electron-positron scattering to produce a couple of muons. This is our lowest order Feynman diagram, which we've drawn already a few times. Our electron and positron annihilate into a photon and pair produce a muon pair. And we can write down our matrix element there. We know that we've got our matrix element here should be proportional to E squared. So our matrix element squared is E to the fourth. And it's quite nice to deal with this in terms of factors of alpha. You have a problem on your problem sheet a bit like this, and I recommend to use alpha to actually make things simpler. Now, let's consider second order Feynman diagrams. We're basically going to add vertices, and it could be something as simple as this one. Our muons in the final state exchange a photon between them. As simple as that. We haven't added any additional initial state or final state particles. This could happen without us knowing it. It's a virtual particle. It's contained between two vertices. We can never actually measure it, but we can see the effect on our final state particles. So, or we could have an initial and a final state particle exchange a photon, or it could be these two, or it could be these two, and on and on. We could add, or you could just have, for example, an emission and an absorption. There's lots and lots of these that you can add. So I've got little dots here because there's lots of different ones that you can add. But all of them are going to have 4 electromagnetic vertices with unit charge particles. So here our matrix elements are all going to be proportional to e to the power of 4. And so our matrix element squared will be proportional to alpha 4. Next, you can add 2 more vertices, again, to give you 6. So you could have, emission and absorption here, there, or both here, or both in the initial state particles. So there's lots of different ones again that you can draw with the 6 vertices. And so your matrix element here is going to be proportional to e to the 6. Now, as we said, like alpha is quite nice to consider here because it's a nice straight number of 1 over 137. As you're increasing the orders of alpha, the increasing orders of these diagrams have smaller and smaller matrix elements that you add to the total matrix element. So usually the lowest order dominates and is the most important, and these higher order ones have small effects. But when we have very precise experiments, like the magnetic moment experiments that measure those very precisely, these higher orders can become important if you need that kind of precision. I would like to go through an example of something here that's, we're going to go back to electron-proton scattering, to electron-proton, and I want to compare it to positron-proton scattering. Okay? And I want to show you how the higher orders affect these two processes differently. Okay, so I'm going to draw a lowest order Feynman diagram here. The electron, we've drawn this already quite a lot. Electron exchanges a photon with a proton. And we've got a factor of E in both cases. Now, this is where I'm going to highlight the need to write down Q. Because Q in this case is negative for our electrons and positive for our protons. And so if we write down our matrix element here, it's going to be proportional to, let's have a look at this vertex here, minus E multiplied by plus E. So it's going to be proportional to minus E squared. Okay. Now let's consider positron proton scattering. So it's the same diagram. I'm just drawing them simply. I'm not including all of the arrows here. But here we've got a positive charge on both sides. And so our matrix element here is going to be proportional to plus E, plus E. So it'll be proportional to E squared instead of minus E squared. Now, when you usually put this into the Born approximation for the cross section, you're squaring your matrix elements, and so these negative factors disappear. But if you want to include higher orders first, these can actually be important. So I'm going to have a look at a higher order here, higher order diagram, i.e. more vertices, where our electron and proton here are going to exchange 2 photons instead. So I'm making it very simple. It doesn't just exchange 1, it exchanges 2. So it's very, very similar to this diagram. But again, we've got 4 vertices here. And it's the same diagram sort of here as well. So here for this higher order diagram, let's write down the matrix element. It's proportional to minus E squared from these ones, plus E squared, which is proportional to E to the power 4, which we know is going to be a much smaller value here. But if we were to draw the same diagram here for our E plus proton scattering, our positron proton scattering, we're going to get the same thing actually, because you'll get plus E squared for your positron vertices and plus E squared for your proton scattering, so proton vertices. So again, it's E to the 4. So these second order matrix elements are the same for electron proton scattering as positron proton scattering, but the lowest order is not, and it's the differences in the way that it mixes. So your total matrix element here, remember that it's the sum of all your matrix elements that you're going to calculate to whatever order you've chosen. And so here you're going to have minus E squared plus E to the power 4. It's going to be proportional to that. And here your total matrix element is going to be proportional to E squared plus E to the power 4. You see that these two are different. And when you put this into your Born approximation for your cross section, sorry, that's supposed to be a sigma, then that's your matrix element squared. And so you're going to have something smaller here to this. You'll have a smaller cross section for electron proton scattering than you do for electron positron scattering, because the higher order the higher order process for electron positron scattering contributes constructively, they interfere constructively, whereas these two interfere destructively. So sometimes the higher orders can be important. And in fact, when we measure the cross sections for electron proton scattering versus positron proton scattering, we do see a difference in the cross sections that we measure coming from these higher orders interfering with the lower orders. Okay, so what I'd like to do next is talk about the running of alpha. We talk about alpha, this it's the fine structure constant. It's a constant. It's a constant that tells us about the strength of the interaction between an electron and a photon. And that should be constant, surely. That shouldn't change, but it does. So what I'm going to draw an analogy with is when we put an electric charge in a dielectric medium. So let's have a look at this here. We've put a negative charge in a dielectric medium, which has polarized around this charge. So it's surrounded by this sort of halo of positive charges. And that has the effect of reducing the charge that we see until we can sort of get past this halo and see the full bare charge of Q here. So it has this screening effect. It's reducing this sort of polarization around it, and all these positive charges are reducing the full charge that we can measure until we can get past them. This is what happens for an electron traveling through space and time. We have quantum effects where the electron can just emit a virtual photon, which can pair produce. We have all these different sort of electron-positron pairs, virtual electron-positron pairs surrounding the electron. Not ones that we can physically probe, they're not real particles, but this is happening at a quantum level. Think about it like the sort of quantum fizz that we have in the vacuum. So we have these clouds of virtual electron-positron pairs that, again, just like the dielectric medium, are going to be polarized with respect to your electron. So the positive charges here are all going to be closer to the original electron than the negatively charged electrons here. This is going to have the same screening effect. Look, there's lots of positive charges here close to our electron, and it's going to screen the bare charge of the electron. If we start to interact with this electron at low energy, we're not going to get past this sort of cloud of positive charges screening the bare charge. Until we start to probe it with higher energy, we can get past this cloud, we can get past this screen and see the full charge of the electron. So from far away, the charge is going to be screened by these the polarized E plus E minus pairs, and it's going to look smaller. As we get past this problematic cloud, we should see a larger effective charge of the electron. So let's try and do that. Let's try and probe the electromagnetic interactions with the electron and photons and see if we can measure larger alphas at higher energies. So we can do this using electron-positron colliders. We're going to annihilate those into a photon, so it's an electromagnetic interaction, and then we're going to produce a mu plus and a mu minus. We can measure the alpha from these interactions because we'll be measuring the cross sections of these interactions, and you'll remember that we had a look at these cross sections. Actually, I've got it here, so I'll try and do this. We found that the cross section of this process should be 4 pi alpha squared over 3s. This is back on slide 11. So it's proportional. Our cross section is proportional to alpha squared, and it should be also proportional to inversely proportional to the center of mass energy. So let's have a look and try and extract alpha from our cross section measurements for differing center of mass energies. What we have plotted here is 1 over alpha, so be careful here. We expect alpha, the strength of the interaction, to increase as we get to higher energies. We're getting past that cloud, and the electron should appear to have a larger charge, i.e. a larger coupling with the photon. So if we're expecting alpha to increase with large energies, we expect 1 over alpha to decrease at higher energies. And this is exactly what we see. If we collide the electron and positron at low energies, for example, down here, we see 1 over 137, our fine structure constant. We start to increase these energies, for example, taking our center of mass energy up to 100 GeV here. So colliding these with 50 GeV of energy each, we should have enough energy to probe small distances and get past that cloud, or start to get past the virtual positron cloud, which is screening the charge of the electron. The electron should look like it has slightly larger charge, and alpha should look slightly larger. And indeed, that's what we see. Here we see that alpha is 1 over 128. Whereas at Q of 0, alpha was 1 over 137. So we do see alpha increase at higher energies, which is really cool. So these coupling constants, these fundamental constants of our electromagnetic interaction, it's not a constant. It runs with energy. You get up to higher energies, you're getting past that virtual cloud, you're seeing a stronger electron charge, therefore it will couple more strongly to your photon. Okay, so here's the summary of QED. You should be quite familiar with it anyway, but we have charged particles interacting with photons. Photons only interacting with the charged particles here. And this coupling constant is alpha. You can relate it to the fine structure constant. The coupling of the photon to these charged particles is proportional to the charge. So with every single electromagnetic vertex, you've always got an arrow going in and out, either electron or a quark, okay, sometimes a W, and a photon. A photon must be involved with the electromagnetic interaction. It's not going to change the flavor of your lepton or your quark. By interacting with a photon, an electron is not going to change into a muon or a quark. So it's always the same flavor and the same charge as well. We're going to conserve charge and energy and momentum through these. And we had a look at this coupling constant, which we can relate to our fine structure constant. We know it's proportional to the electric charge of our lepton or our quark that we're looking at. And we've seen that it runs with energy scale. At higher energy, you can get closer to your charged particle, past the virtual cloud of particle-antiparticle pairs, and see a larger charge for that bare particle. And I hope that I've shown you that this is QED has been tested to very high precision, both with magnetic moments of electrons and muons, and then also, of course, with this running of alpha, which was a fantastic prediction, and that has been verified. Okay, so that wraps up QED. We're going to move on next to chapter 7 and deal with the strong force, which is called quantum chromodynamics. Thank you.